astrophysics allows us to examine the nature of events light years away from the Earth, teaching us everything from how the universe began to what happens when a star dies. But understanding these events is dependent on being able to observe the messengers, everything from cosmic rays to gravitational waves, that they emit. Collecting and interpreting these messengers requires a wide range of infrastructure, technology, and expertise. Japan's Institute of Cosmic Ray Research is already making this a reality.
The observations of cosmic rays, gamma rays, neutrinos, gravitational waves, and so on tell us the mechanism of various high-energy phenomena in the universe, such as the supernova explosion and the acceleration of cosmic ray particles. The Institute for Cosmic Ray Research is an inter-university research institute trying to explore the frontier of the cosmic ray physics, astrophysics, and elementary particle physics with the observation of multi-messengers. We collaborate with many researchers from Japanese and overseas universities.
In Japan, Kamiokande Observatory is one of ICRR's key research centers and home to the world-renowned Super Kamiokande, an experiment looking at solar supernova and atmospheric neutrinos.
Super Kamiokande is a 50,000-ton so-called water Cherenkov detector. So its height is 42 meters, diameter 39 meters. Totally 50,000 tons of water is filled in the tank. Elementary particles, for example neutrino, come to the tank and interact, produce on some particles. They emit Cherenkov light. That light is detected by this Super Kamiokande. Atmospheric neutrinos produced by cosmic rays, and in the atmosphere, neutrinos produced. So using those neutrinos, we discovered neutrino species change. It's called oscillation. There are three different modes of neutrino oscillation. The Super Kamiokande discovered all those three oscillation modes. The most important outcome of the discovery of neutrino oscillation is that neutrino must have masses. In the standard model of elementary particle physics, neutrinos are massless. We would like to investigate what's the model beyond the standard model. One of the ways is to search for so-called CP vibration. So by measuring neutrino oscillation and compared with anti-neutrino oscillation, we can investigate CP vibration.
On the other side of the world, in the desert of Utah, USA, the Telescope Array experiment is looking at ultra-high-energy cosmic rays and improving our understanding of their association with cosmic sources.
The Telescope Array experiment aims at measuring the energy spectrum and arrival directions and the mass composition of ultra-high-energy cosmic rays. Using 507 surface detectors, we collected data for 5 years and found evidence of anisotropy. We don't know the actual source, so in order to improve our data, we plan to quadruple the area of the telescope array. For the new site that we call TA times 4, we plan to deploy 500 detectors, but with a wider spacing, 2.08 kilometers. We expect a class of a large and energetic structure in the universe. One candidate is active galactic nuclei, which are suspected to have at the center supermassive black holes.
In the Atlantic Ocean on the island of La Palma, the ICRR is working on the Cherenkov Telescope Array in order to observe high-energy gamma rays an order of magnitude better than has been possible before.
High-energy gammas give more intense Cherenkov light. By using the orientations of multiple Cherenkov images, we can estimate the arrival direction of very high-energy gamma rays. Cherenkov Telescope Array is a next-generation observatory for high-energy gamma ray observation. More than 1,200 scientists from 32 countries are participating in the CTA project. ICRR will be responsible for the delivery of high-precision segmented mirrors covering the dish area of 400 square meters, high quantum efficiency optical sensors, and ultra-fast readout electronics. So far, the foundation to first large-size telescope of CTA has been built. We aim to complete the whole CTA in 2022 when we will begin full operation. We can observe the universe under extreme conditions like supernova remnants, active galactic nuclei, and gamma ray burst. There is also the possibility of observing dark matter, which constitute a significant mass of the universe.
Back underground in Kamioka, the ICRR is in the process of building the large-scale cryogenic gravitational wave telescope, or KAGRA, in order to contribute to the exclusive and challenging field of gravitational wave observation.
KAGRA is fundamentally a huge microsome laser interferometer. It utilizes Kamioka underground site and cryogenic mirrors to realize high sensitivity. Underground site is useful for silent and stable environment. Cryogenic mirrors are good for small thermal noises. If gravitational waves pass through KAGRA, one arm will be short and another arm will be long. So we can detect the gravitational waves to measure the difference between the two arms by interferometer. I think that we will be able to start a KAGRA observation run in 2020. When KAGRA has enough sensitivity to detect the gravitational waves, LIGO, Virgo, and KAGRA will make triangular surveying network to get the direction of gravitational wave sources. It is essential for gravitational wave astronomy. I hope especially to detect nearby supernova explosion with Super Kamiokande neutrino telescope. Those observational results will resolve the physics in high-density stars like neutron stars.
With these exciting projects and many more going on all around the world, ICRR is poised to improve our understanding of the universe by leaps and bounds.
The research in ICRR will have a huge impact on the understanding of various high-energy phenomena in the universe that can be studied only with multi-messenger approach. We provide the data. We hope that the global astrophysical community uses it, and in the end, we'd like to understand the universe better.